This video will focus on solving the 2D Laplace equation using finite differences. We will translate continuous calculus into discrete linear algebra using Python and the scipy.sparse library. The core question is to solve Laplace's equation over a square region with specific boundary conditions. Our tasks include discretizing the domain, setting up the finite difference equations, solving the resulting linear system, and plotting the potential. We are solving Laplace's equation, represented by nabla squared equals 0, over a square region. The problem is driven by 4 boundary conditions along the edges of the square. The numerical workflow involves 4 steps. Discretize the continuous square into a grid, set up the finite difference formulas, solve the sparse linear system a phi equals b, and plot the result as a contour map. The overarching strategy is to translate the partial differential equation into a single sparse linear system. We discretize the domain, form the stencil matrix, apply boundary conditions, solve the system, and then plot the output. Step 1 is sampling the continuous space by dividing the square into an n times n grid, here 50 times 50. Uniform spacing, set by dx and dy, simplifies the finite difference stencil and improves mathematical stability. Step 2 is bridging 2D physics with 1D solvers. The linear algebra solver requires a 1D vector of unknowns. We map the 2D grid index, I, j, to a single 1D vector position k using row major order, k equals I, plus jcdotn. The indexing challenge requires flattening the 2D spatial coordinates into a 1D vector. This mapping is essential for the computer to assemble the matrix equation a phi equals b correctly. Step 3 involves approximating the second derivatives. We replace the continuous Laplace equation with central finite differences in both the x and y directions. Combining them results in the 5-point stencil, where each interior point links to its 4 nearest neighbors. This diagram illustrates how a single grid point translates into a row in the matrix system. The interior points form the matrix A in deep cobalt blue, and boundary values become part of the right-hand side vector B in vibrant burnt orange. Our objective is to move from continuous physics to a computable problem. We convert the continuous surface into a discrete grid of points, translating spatial relationships into the linear algebra equation a phi equals b. Let's examine the anatomy of a single interior point. The finite difference Laplace equation for this point involves its value and the values of its 4 nearest neighbors, separated by dx and dy. By defining the grid spacing coefficients a, x, and a underscore, we can rearrange the math to isolate the unknown values of phi. This matrix-friendly form groups the coefficients for the central point and its neighbors. The magic trick for handling boundaries is recognizing that if a neighbor is on the boundary, its value is known. Known boundary values are moved to the right-hand side vector B. Unknown interior values stay on the left in matrix A. To vectorize the grid, all interior points, nx in the x direction and ny in the y direction, are stacked into the unknown vector phi. This is done by ordering them row by row, from phi 1 up to phi nx and y. Stacking points row by row creates a highly structured, sparse, block tridiagonal matrix A. The internal blocks B represent the x-direction connections, while identity matrices, scaled by a y, represent the y-direction connections. In the special case where grid spacing is equal, the equation simplifies. The value at each interior point is simply the average of its 4 neighbors. In matrix form, diagonal entries become 4, and connected neighbors contribute -1. Let's look at an example with a small 2 times 2 grid, resulting in 4 interior unknowns. The assumptions are a uniform grid and a left boundary value of 1, with all other boundaries set to 0. We assemble the matrix using the uniform grid simplification and solve the system. The results show that the points closer to the boundary value of 1 have a larger potential, confirming the physical intuition of the solution. Step 4 involves assembling the matrix a phi equals b. The finite difference equation for each interior point is represented as a linear system. Each row in A corresponds to an interior point, with coefficients for neighboring grid points. This includes the diagonal entry, coefficients for the 4 neighbors, and a zero source term in B. Step 5 is dictating the boundaries. Boundary rows are replaced by simple identity equations. We don't solve for boundaries, we dictate them. Replacing the matrix row with A equals 1 forces the solver to obey the given physical value exactly, such as phi equals 0 or phi equals sine pi y. To enforce Dirichlet boundaries, we hard-code known boundary values using the identity matrix. The diagonal element AKK is set to 1, and the corresponding BK is set to the known boundary value. This simplifies the equation to 1.phi k equals known value. Coding the edge cases involves setting up the boundary conditions. For zero boundaries, like the left, top, and bottom, A is 1 and B is 0. For the sine wave boundary on the right edge, A is 1 and B is sine pi y. A deep dive into sparsity shows that for a 50 by 50 grid, the matrix A is large, but each interior row only has up to 5 non-zero entries. We use the list of lists, or LIL, format for incremental row-by-row assembly. It is then converted to compressed sparse row, or CSR, format for high-speed linear solving. Step 6 is solving the linear system A phi equals B. The SP-solve function efficiently solves this sparse system. This single line of code is the precise moment the partial differential equation, or PDE, is fully converted into a computed numerical field. Step 7 is reshaping and visualizing. The 1D array is reshaped back into a 2D physical field. A contour plot, like this potential heat map, provides the visual form of the computed solution. Interpreting the computed physics through vertical slices shows how the solution approaches the sine pi y boundary. The interior field changes smoothly, with no abrupt jumps. This represents a perfect physical compromise between all 4 pinned walls. In summary, the process moves from the continuous theory of the PDE to the discrete rule of the logic, to the computational engine of A phi equals B, and finally to the physical result displayed in pixels. This is a textbook example of numerical modeling.